Today we're going to talk about an area of thermochemistry called calorimetry, and this is the measurement of heat. Now, one of the things we've got to remember is that temperature and heat are not the same thing. Temperature is simply a measure of the average kinetic energy of particles in a substance. There are three temperature scales that we use. One of them is Fahrenheit. It's based on the boiling and freezing points of alcohol. Celsius, the one we use most often in science, based on the freezing and boiling point of water. And when we get into the gas laws, we'll be using a system called the Kelvin scale, and it's based on something called absolute zero. And absolute zero is a temperature at which there's absolutely no molecular motion. It's the coldest possible temperature that you can have. So one of the things that we often do is convert back and forth between Kelvin and Celsius. I don't even teach converting between Fahrenheit and Celsius or Fahrenheit and Kelvin because we just don't use Fahrenheit in science. So for Kelvin, you simply take Celsius and add 273. For Celsius, you simply take Kelvin and subtract 273. And the thing that I always remember is if you think about the ABCs, you've got ABC, blah, 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 K, L, M, blah, 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 Z. Then if you want to think about it this way, K is a bigger letter, at least it's further to the right, than C is. So K is always going to be the bigger value when we're talking about Kelvin versus Celsius. So when you're trying to find Kelvin, it's always going to be bigger than Celsius, so you're always going to add the 273. If you're trying to find Celsius, Celsius is always smaller than Kelvin. So if you're given Kelvin, you're going to subtract 273 to get to the degrees Celsius. So that's the temperature, that's the way we convert for our temperatures. So if we have a gas that has a temperature of 90 degrees Celsius, what's the Kelvin temperature? Well, if we know that Kelvin must be a bigger value than Celsius, then we're going to know that we need to add that 273 and get 363. And notice something, kelvins. It's not degrees Kelvin. Don't put a degree symbol with that. It's not correct. It's 363 kelvins. If we want to take 150 kelvins and change that to degrees Celsius, we know that Celsius is smaller, so we're going to take that 150 kelvins and subtract the 273, and we end up with a negative 123 degrees Celsius. So the first part of your worksheet will be involving that conversion between Kelvin and Celsius. I do want you to know some of the common temperature values in Fahrenheit, Celsius, and Kelvin: the boiling point of water, the freezing point of water, and absolute zero is what it really should say there, absolute zero. So the boiling point of water, 212 degrees Fahrenheit, 100 degrees Celsius, and of course add 273 to that, 373 kelvins. Our freezing point of water is 32 degrees Fahrenheit, 0 degrees Celsius, and 273 kelvins. For our absolute zero, it's 0 kelvins, which subtract off 273, and we get negative 273 degrees Celsius. That's a whopping 459 degrees below zero in Fahrenheit. So those are just some temperatures that I want you to be familiar with. Mainly, I really want the values here, and of course, I want you to know that 0 kelvins is absolute zero, so I want you to know that as well. Now that's temperature. Heat, on the other hand, is the total amount of kinetic energy in a material. You measure that in calories and joules, not in degrees Fahrenheit or Celsius or kelvins. It's in calories or joules. Calories, the amount of heat it's required to raise the temperature of 1 gram of water 1 degree Celsius. This is an important conversion factor that you'll need because we'll be doing that conversion periodically. And as I just said, they are not the same. Temperature and heat are not the same. Do a cup of boiling water and a swimming pool of boiling water have the same temperature? The answer is yes, they have the same temperature because they're both boiling. So they're both going to be 100 degrees Celsius. Do they have the same heat content? Well, ask yourself, do you want to have a cup of boiling water or a swimming pool of boiling water poured on you? And the answer is, well, of course, the swimming pool of boiling water will have way more heat content and burn your body much more to have that poured on you than a cup of boiling water. So the same heat content, no, and that's because the masses are different. Heat involves mass. Temperature does not. Heat involves mass, or the amount of heat content involves the mass of the substance you're dealing with. Temperature does not. It's very important to realize. So how do we measure temperature? Well, heat. We need to know the specific heat capacity of a material. Now, every material is different, and you know this. You know that if you had a pan, a metal pan sitting outside in the hot sun, and a metal pan with water in it sitting out in the hot sun, you know without a question which one you'd rather step into. You know you'd rather step into the one with water in it because you know that the water won't be as hot. Its temperature won't be as high as the metal pan with no water in it. That's important because every material rises in temperature at a different rate. They've both had the same amount of heat energy put into them if they've been outside the same amount of time in the sun side by side. But the temperature of the metal has risen much more quickly than the temperature of the water. Metals tend to have low specific heat capacities. What that means is they raise and lower their temperature very quickly. Liquids, especially water, tend to have very high specific heat capacities, and they take longer to change in temperature. They're very sluggish, and people in coastal areas know that this is true because the ocean water cools down and heats up much more slowly than the land. That's what keeps those coastal areas much more moderate, changing in overall temperature much more slowly than other areas. So once we know that there is a specific heat capacity for each material, and if you'll look in the back of your notes, there's a table, and I give you some values that are in calories per gram, and this calories per gram Kelvin is the same thing as a calorie per gram degree Celsius. Same thing over here. Joule per gram Kelvin is the same thing as joule per gram degree Celsius. And you can use either one of those units depending on what temperatures they give you in the problem. 1 degree Celsius increase in temperature is the same thing as 1 Kelvin increase in temperature. If you start out at 100 degrees Celsius, which is 373 kelvins, and you increase by 1 degree, 101 degrees Celsius, that's going to be 374 kelvins. So the change of 1 degree Celsius and the change of 1 Kelvin is the same unit change. Now, 1 degree Celsius and 1 Kelvin are not the same temperature. If you go outside in 1 degree Celsius, you'll be shivering and you'll want a coat. If you go out in 1 Kelvin temperature, you'll be dead. So the change, though, is the same. Okay. So an example, how many calories of heat, oh, well, I guess it would be nice if I talked about the equation first. The equation is that Q is equal to MCAT. That's how we say it in chemistry, the MCAT equation. Often it's written as MC sub P AT, but often the P, that subscript P is left off, I guess because it works better with our MCAT little thing that we say. But Q is heat, and heat can be in calories or joules. M is mass in grams. That delta sign in front of the T, we've seen that delta before. It's for change in temperature. And then C sub P, or C, is the specific heat, and that's the one you have to look up in a table. So how many calories of heat are required to raise the temperature of 25 grams of aluminum from 14 degrees Celsius to 22 degrees Celsius? The first thing you need to do is figure out what it wants you to find. How many calories of heat required to raise the temperature of 25 grams of aluminum, so it gave us the mass, from 14 degrees Celsius to 22 degrees Celsius. Now, to get the change in temperature, it's always final minus initial. So in these problems, you're going to take the final temperature minus the initial temperature. So the delta T is going to be the 22 degrees Celsius minus the 14 degrees Celsius, which in this case is going to give us an 8 degrees Celsius change in temperature. So that's our delta T. So solving for Q, it's asking for heat. Q is equal to MCAT. It gives us the value for the mass. It tells us that we have 25 grams. Now, as far as the value for C, the specific heat, remember we have to look this up. Now, this time it wants the value in calories. So if it wants that value in calories, then we need to make sure we're using the correct column. We want the calorie column back here. And for aluminum, that's 0.21 calories per gram Kelvin, or calories per gram degree Celsius. Since they gave it to us in degrees Celsius, we're going to write this down as 0.21 calories per gram degree Celsius. If they'd given us Kelvin, we would have put Kelvin there. Remember, the unit change is the same. The change in temperature is 8.0 degrees Celsius. We just figured that out. So when we multiply that out, we end up with 42 calories. Looks like we need 2 sig figs, since every one of those values has 2 sig figs. We end up with 4.2 times 10 to the first calories. Now, what if they wanted us to change that to joules then? One of the questions on your paper asks you to do that. Well, then we're going to take that 42 calories, and if this were carried out further, remember we don't want a rounded value. Go back to your conversion. Remember we said that 1 calorie was equal to 4.18 joules. So calories cancel. And we get 175.56, excuse me, 175.56, which to 2 sig figs again, and correct scientific notation, would be 1.8 times 10 to the second joules. So if it does ask you to convert to joules, then make sure you do that. Okay, on the next one, how much heat in joules is released when 175 grams of ethyl alcohol cools from 328 to 303 kelvins? We want heat in joules this time. Our delta T is going to be final minus initial, so 303 minus 328. Look what the value is going to be now. We're going to have a negative 25 kelvins for our value. And solving for Q, again, Q equals MCAT. Our mass value is 175 grams of our ethyl alcohol. We want this in joules this time, so let's look back here at ethyl alcohol in the joule And grain alcohol and ethyl alcohol are the same thing. It's 2.4 joules per gram. And we're going to want to use Kelvin this time since we're dealing with kelvins in our temperature. 2.4 joules per gram Kelvin. And our delta T is negative 25 kelvins. It's cooling down, so we're losing that heat. When we multiply this together, we end up with negative, very important, negative 10,500. Now, technically, I guess that should be in green because you don't have to put the interim value, but we do have grams canceling, kelvins canceling, so it looks like we're left with joules here. And we want that to be in scientific notation, sig figs. So it looks like our smallest number of sig figs is going to be 2. So this comes out to be negative 1.1 times 10 to the 4th joules. That means we've given off that much heat energy, which was indicated when it said that we cooled it. Okay, our last one. This time it's asking us to find the specific heat capacity of olive oil. It gives us a heat value, gives us the mass of the olive oil, tells us we start out at 21 degrees Celsius and it increases to 85. So the first thing we want to do is get that delta T. The change in temperature is going to be 85 degrees minus the 21 degrees, which is going to give us a 64 degrees Celsius change for our delta T. Q equals MCAT. Okay, we want to solve this time for specific heat. So we're solving for C. So what we're going to do is divide both sides by M and delta T. So it's going to reduce to 1 on this side. We're going to end up, I like my variable to be on the left, that C is Q over M delta T, or Q over MAT. When you solve this, make a note to yourself that solving for any of these, if we solve for M, we're going to get Q over CAT. We just solve for C. If you solve for delta T, you're going to get Q over MC. So I've told people to think of Q as the queen. It's always going to be lording it over everything else. It's always going to be on top of everything else. So keep that in mind because on your worksheet, you're going to be solving for different variables. And we're not going to cover problems involving all of those possible ways to solve. So make sure you know how to solve for those different variables. So C then is going to be our Q value, which is 435 joules, divided by our mass value, which is 3.4 grams, and our delta T value, which we said was 64 degrees Celsius. And when we solve for this, we get that C. Now, when you put this in your calculator, make sure you put it in correctly. It's 435 divided by 3.4 divided by 64. They're both on the bottom, so you make sure you divide by both of them. When you do that, you get 1.999. I believe there's another 9 involved. Regardless, it looks like we're going to need 2 sig figs from these values. So our answer becomes 2.0. Nothing cancels. So joules over gram degrees Celsius will be our final answer.